So differential equations. An equation involving a derivative is called a differential equation. So if we begin with dy dx, we begin with the derivative. That's a differential equation. Sometimes it's easier to figure out how fast the things are changing rather than where they are at a particular time. We can come up with equations that describe how things are changing, sometimes easier than we can with what's happening now, what's happening now, what's happening now. Describe how something is falling rather than where it is. Does that make sense? Sometimes it's that way. Okay, and we can use rates of change and stuff. That's what a differential equation is. They can get very complex. There are courses that do just differential equations, and they take what we do in here to a much higher level. It is probably the one math class I regret not taking. I didn't because I didn't have to, and I was a returning student. I had already had a wife and child, and I went back and got my math degree and teaching credential, and I didn't want to spend more time in school than I had to. So if I didn't absolutely have to take it, I didn't. Probably that's the one I regret not taking, but I also didn't think I'd be teaching AP calculus either. Because that helped me teach, because it's the next closest thing to calc. The order of the differential equation is the highest degree involved in the equation. Okay, so you can do a second derivative, third derivative, same idea. One method of solving a differential equation is to use antiderivatives / integrals, and that's what we are going to begin with today. We're going to start with that method. Okay, find the general solution to the differential equation. Dy dx equals secant squared x plus 2x minus 5. Now, basically what we're doing is we're looking for y. We want y equals. We want to go backwards. So technically what we're doing here, what is the inverse of the derivative? What's the inverse of the derivative? The integral. Integrals and derivatives are inverses of each other. So if I want to take, I can do whatever I want to both sides. The inverse of the derivative is the integral. So if I integrate both sides, I solve my problem. The integral of dy dx, actually, let's back this up. Time out. I always forget it with the simple ones like this, and I do say simple ones like this. First thing we'll want to do is we want to get dy's and y's on one side, dx's on the other side. So what I want to do is I want to get rid of my dx. I'm going to multiply both sides by dx. So I get dy equals secant squared x plus 2x minus 5 dx. And technically, that's all in parentheses. And I forget this at this level, but I won't forget it when we get to the harder stuff later. Because that will become a much more important step later. Okay. Now, I want to solve for my derivative. I want to get y. I want to get x. So what do? I integrate both sides. Because the integral is the opposite of the derivative. So the integral of dy is y. What's the antiderivative? How many dy's do we have? We have one dy, right? What's the antiderivative of 1? Y. Because we're doing it y, not x, right? Same thing on the next one. Take the antiderivatives. How do you solve the integral? Take the antiderivatives. Antiderivative of secant squared. Tangent x. Tangent of x. Antiderivative of 2x is what? X squared. Antiderivative of negative 5. Negative 5x. And then what else do I need to have? Plus c, because I am doing it for a general antiderivative. This is one of an infinite number of possibilities. What is the only thing that will change within my infinite possibilities, though? The constant. Plus c handles any constant. And remember, if I take the derivative of the antiderivative and I get what I started with, it works. There's an infinite number of numbers that c can be. Any infinite number, choice for c will work. So I technically have a family of antiderivatives. This is why it's the general solution rather than a specific one. I'm not looking for the specific original equation. I'm looking for the general antiderivative. Okay? That's that.
Where does the dx go?
When I took the integral dx, when I take the antiderivative, it goes away. Okay? Just like when you did integration in the last chapter, it goes away. Okay? I'm integrating 1 with respect to dy, with respect to y. I'm integrating this side with respect to x. So I do the antiderivative with respect to x. Okay? These will get stepped up, but the first will start out pretty easy like this, relatively speaking. Okay. Find the particular solution. Slightly different problem, same basic idea. Find the particular solution to dy dx equals e to the x minus 2 with the initial condition x equals 0 and y equals 5. That means we're looking for the antiderivative, the original equation that gives us that derivative that passes through the point 0, 5. There's only one that passes through the point 0, 5. So we need to find that one. Well, to find that one, you start out the exact same way we did the other one. dy dx equals e to the x minus 2. Multiply both sides by dx, get your y's on one side, x is on the other. And then take the integral of both sides. Y equals the antiderivative of e to, that's supposed to be e to the x, not e squared. Antiderivative of e to the x is e to the x. Antiderivative of negative 2, negative 2x. And then I have to have my plus c. This is my general solution. How do I find my specific solution? I plug in x and y, 0 for x and 5 for y, and solve for c. So I go, okay, using my initial condition, 5 for y, 5 equals e to the 0 minus 2 times 0 plus c, and I solve for c. I solve for that particular value of c that meets that particular initial condition. Okay. E to the 0 is 1. 2 times 0 is 0. So I have 5 plus 1 equals c. That means c equals 4. 6. 5. Oh, sorry. 5 equals 1 plus c. My bad. My bad. My bad. But we can check the tape. We can do instant replay. We don't want to do that. Okay. So this is my general. My specific answer would be y equals e to the x minus 2x plus 4. That is the specific solution. The specific antiderivative that passes through the coordinate 0, 5. That's what that is. Okay. Fairly simple. All the ones you have are all x only at this time. So you'll end up with y equals something x. Okay, y equals something x, that's what you'll end up with. Okay. You may have some that are general, plus c. You may have some specific, plug in x and y to find c. Okay. We will be stepping these up in difficulty, but that will come closer to the end of this chapter. Okay. Now, there is another way to solve differential equations. Slope fields. Do not try to copy this down. We will be doing slope fields tomorrow. I got a worksheet for you to do slope fields, but you will see the slope fields. Now, but I do want to talk about them. Okay. Differential equations can also be solved using a slope field. What a slope field does is it gives you all the possible solutions to your equation in one thing. What it is that each dash represents the value of the differential equation. So let me go ahead and scroll on this one. Okay. So for example, this equation is dy dx is equal to x minus y. Every single dash is a line, a little tiny line, each dash a little tiny line that has the slope of what the x coordinate minus the y coordinate is. So wherever the x coordinate and the y coordinate are equal, what do I get? 0. dy dx is 0 when the x coordinates and y coordinates are same. 1, 1, 2, 2, -3, -3, right? So look at all these nice little horizontal slashes. Those happen where the x and the y coordinate are the same. That's why they're little horizontal lines, because they all have a slope of 0. Wherever the x coordinate is 1 more than the y coordinate, I have a little dash with the slope of 1. Wherever the x coordinate is 1 less than the y coordinate, I have a little dash with the slope of -1. These represent all the possible solutions. Now, we can do the antiderivatives, and we'll learn how to do antiderivatives with x's and y's mixed later on. But sometimes you can't take antiderivatives of your differential equations, and a slope field is the only solution. Okay, and that's where those are useful. We won't do that on all of them. Okay. So these are all the solutions. These are every single plus c. Let's say I want to find a particular solution. Let's say I want to find the one that goes to the point 0, 2. So I go to where 0, 2 is on the graph. And I kind of sketch following along. I do what the dashes tell me. So I go this way and it goes up. And then I go like this. And it goes like that. There's a particular solution passing through 0, 2. Let's say I want to do a particular solution passing through 2, 0. Go 2, 0. And I go, okay, so the dashes tell me I go like this. And then I go about like that. You just follow the dashes as best you can. Okay, and your calculators will do this. Okay, I don't know if the Casios will or not, but it doesn't really matter. But I know the TIs, particularly the 89s, and I think the 84 pluses will also do this. I'm not positive. If you want to know, go online, Google how to do a slope field on my calculator and type in what kind of calculator you have. Because smarter people than me have shown how to. I used to have a worksheet on how to do it on the 89s. The 83s used to not be able to do it. The 83s might. The 84s, I think, can. Okay, and you can actually get these pictures, and you can tell it to go through a particular point, and it will sketch in and follow the particular point. It's really kind of cool. Desmos does not do this. It's one of the things I wish Desmos did. They don't do this. They need to fix that. Okay, there is another program that does, but I have to get it hard installed, and I haven't been able to do that. So, okay, but that's what it is. And this is the same one here. What does this look like? Each one of these, I pick a point, I go, okay, follow it along, and it kind of goes like that. And when I pick a point here, and I follow it along, and it goes like that. You can kind of get an idea what the equations are going to look like. This one looks like an exponential. Okay, exponential growth, starting with a negative out in front, exponential decay. Actually, just growth inverted. Okay, that's what they look like. We will be doing these as part of the worksheet I did. Okay. And no, I will not make you do every single point, but you will be doing a few. Okay. Questions?